Hello and welcome to the Analog Devices Precision Training video, which focuses on switch and multiplexer technology. This video is the sixth in the series entitled VT1006, Switch Fault Protection. In this video, our learning objectives are the following. First, understanding the different causes of overvoltage events. Second, learning how to protect a precision signal chain from overvoltage fault risks while preserving precision performance. Last, familiarizing yourself with the fault protection switch family. When operating in a harsh electromechanical environment, it is impossible to isolate systems from common causes of faults or overvoltage fully. These common causes include the following. First, installation error. This occurs due to incorrect system wiring during installation. Second, loss of power. Customers are very interested in this. If a system loses power but voltage is still on the input, it can exceed the maximum device ratings and lead to electrical overstress. Third, user miswiring. This is common in large rack systems with multiple inputs/outputs and supplies that need to be connected and disconnected frequently. Fourth, user error. A typical example is selecting a micro voltage range on an instrument and then applying tens of volts to the instrument input. Last, power supply sequencing. Similar to loss of power, this occurs when the system receives a signal before being powered up. This is an example of a precision signal chain taken from the Vibration Data Acquisition Circuit Note, CN0540, available on www.analog.com. In this signal conditioning example, the piezo transducer is on the left, followed by a protection switch. This switch must have excellent precision performance to avoid signal degradation and loss of system sensitivity. This part of the signal chain is where overvoltage protection and detection need to take place to protect downstream ICs. Additionally, it is typical to have high ESD robustness at this input stage of the circuit. Overvoltage protection means the input voltage to the switch is greater than the supply voltage. If this happens, the electrostatic discharge, ESD protection diodes to the rails will be forward biased, causing high current flow to the supply rail and potentially leading to burnout. Traditionally, up-down clamping diodes and a series of current-limiting resistors are used to prevent this. However, there are several drawbacks such as high channel resistance, overvoltage current being shunted to the supplies, clamping diode leakage affecting precision measurements, and no protection in the power-off state. The best solution is to use a precision switch with integrated overvoltage protection. The advantages include tolerance to fault voltages up to ±55 volts, no need for an external bomb, blocking of overvoltage fault current from the supplies, low and flat series resistance, low leakage maximizing precision performance, and guaranteed overvoltage protection even when the circuit is powered off. This section delves into the architecture of the overvoltage protection switch. It features a special ESD protection cell on the input that not only protects but also tolerates overvoltage events. The switch input is monitored, and when it exceeds VDD or drops below VSS, the switch will automatically open. The switch can tolerate fault input voltages up to ±55 volts. Note the regular ESD protection diodes on the output of the switch. Some fault protection switches are only overvoltage protected on the input, while others have protection on both the input and output pins. This is an example of an overvoltage protection switch called the ADG5421F. It is a dual SPST switch. The diagram shows the part configured for use in our example signal chain. It protects against overvoltage events from the sensor input. AC decoupling capacitors are needed on VDD and VSS to keep distortion low and maximize the power supply rejection ratio. The fault flag, FF digital output pin, is connected to an LED and a microprocessor, so that an overvoltage event can be recorded and data can be ignored as needed. Note the 0-ohm resistor in series with the switch. This facilitates debugging by enabling the switch to be bypassed. In the final version of a PCB solution, this resistor would be removed. Another flexible output protection solution is to use an overvoltage channel protector component like the ADG5462F. The figure here shows a typical setup where a high voltage plus-minus 15-volt amplifier output is connected to a low voltage 5-volt ADC. The channel protector in the center is normally on and will automatically go open circuit when its input exceeds the reference voltages at the pause FV and neg FV pins. In this case, the reference voltages are plus 5 volts and 0 volt. Note that when the input voltage returns within the reference voltages, the channel turns back on again. No logic control or additional setup is needed for these channel protector products to operate. Here is a summary of the switches and multiplexer fault protection family. The family consists of 15 generics, covering many configurations from single-pole, single-throw switches to 8-to-1 multiplexers. All devices in the family feature overvoltage protection up to plus-minus 60 volts and overvoltage detection capabilities, protecting sensitive systems from damage in harsh environments. The devices offer a wide supply voltage range, from plus-minus 5 volts to plus-minus 22 volts for dual supply or plus 8 volts to plus 44 volts for single supply. There is also a low voltage option, the ADG7421F, with a supply range from plus-minus 1.8 volts to plus-minus 2.5 volts for dual supply or plus 1.8 volts to 5 volts for single supply. In summary, first, overvoltage is a widespread cause of device damage. Second, integrated overvoltage protection reduces system design overhead. Last, a full family of products is available to suit various design requirements. Please visit analog.com/switches multiplexers to see examples of switches on offer.